Hi everyone, welcome. Welcome to the C3 AI DTI seminar series for the full semester. My name is Richard Zhang, and I am an assistant professor at the University of Illinois. And I'm co-organizing and co-hosting the seminars series with Gary Joshi, who is an associate professor at Carnegie Mellon University. C3 AI DTI features research that focuses on studying how artificial intelligence, machine learning, and big data can lead to scientific breakthroughs with large-scale societal benefits. And before we begin, we would like to pause to acknowledge the support from our academic and industry partners, for which we are deeply grateful. So our fall 2022 series is organized around two special themes: adversarial machine learning and distributed and federated learning. Our talks are scheduled to alternate between these two themes over alternating weeks. We're wrapping up the semester at this point, so we have a very exciting speaker today, Nicolas Carlini, and to wrap up the semester, we have Gary Joshi, myself, and we'll be hearing from Siwoo O from University of Washington at the very end of the semester. And the abstracts for the future talks, as well as the recorded talks of previous speakers, will all be available on our YouTube channel, and we invite you to subscribe to our newsletters and our channel so that you don't miss these very exciting talks. So today we're very happy to welcome Dr. Nicolas Carlini to share his research with his talk entitled Unspecified Foundation Models Considered Harmful. Nicolas Carlini is a research scientist at Google Brain. He studies the security and privacy in machine learning. For this, he has received best paper awards at ICML, Usenix Security, and IEEE SMP. Carlini earned his PhD from the University of California, Berkeley in 2018. So the format of this presentation will be 50 minutes of the talk, and afterwards we will have 10 minutes of Q&A. We invite the audience to ask your questions using the Q&A feature, and we will ask them at the end of the session. Please upvote questions if you want to hear the answers to them. And without further ado, I'd like to invite Dr. Carlini to begin his talk. Thank you very much.
Yeah, thank you. Yeah, I'm really excited to be here. I think this is you've had a wonderful collection of talks. I've enjoyed listening to a couple of them. Yeah, so I'm excited to talk about some work that we've been doing recently, looking at what people are calling foundation models. I don't know whatever you want to call them, big giant machine learning models. And I'll define the underspecified piece in a little bit and sort of explain to you why I think that things are not in a great state for security right now. Okay, so let's get started with a little bit of history. So let's imagine the year is 2014. Someone tells you they have a new algorithm to generate synthetic images. They might be able to show you images that look something like this, where, if you kind of squint, you might recognize that this kind of looks like a human face just a little bit. These are very low resolution, grayscale images that really, I mean, it was impressive at the time, but looking back at it today, it's quite bland. But machine learning advances really, really quickly. It's been less than 10 years since that. And if someone told you the same thing, that they have an algorithm to generate synthetic images, they could generate images that look like this today. Where here, not only have we just gotten an image, we've actually asked for a particular image. Like the researchers of this paper asked for a photo of a corgi riding a bike in Times Square wearing sunglasses and a beach hat. And here, I mean, you have a corgi riding something. It's almost like a bike. It's kind of hard to tell, but you can sort of noticeably describe this as Times Square with sunglasses and a beach hat. So like, it's really impressive what machine learning models have done over the last couple of years. And this is what we're sort of used to in machine learning. We're used to this world where things get a lot better over time. And what I'm going to do in this talk is tell you about one specific case where it looks like machine learning is getting worse over time, not better, right? Which is surprising. Like normally, like, we're in this world where things don't get worse over time. They get so much better. Like, like it's very hard. Like if you had showed this image on the right to anyone 10 years ago and told you a neural network generated this, I don't think they would have believed you. Like we're sort of so far away from this, but like we sort of have made huge progress. But at the same time, I think we're also making things much more vulnerable. And that's what I'm going to try and talk about today. Okay. So I'm going to sort of have sort of a bunch of background at the beginning just to sort of catch everyone up, and then I'll go into the talks and the attacks in the second half of the talk. So why should things be vulnerable? Basically, the argument that I think what really comes down to is the fact that deep learning is essentially inscrutable. We don't know why machine learning works. And when you don't know why something works, it's usually very easy to attack it. And the harder you make something to understand, the more vulnerabilities that will exist. I think this is sort of a fundamental truth in security, and it is true in machine learning as well. Now, when I tell people, deep learning is inscrutable, people often tell me, yeah, but there are lots of things in the world that are inscrutable, and it's okay. Here's a C program. This C program is inscrutable. All right, right? Does that matter? No. I mean, what the C program does is it calculates the area of this circle by taking the radius over the circumference. But this is fine. No one uses this C program to do anything meaningful. If NASA was going to design spacecraft that launches around this calculation of pi, maybe that would be a problem. But they don't, so we don't care about it. This is not the area we're in with machine learning, because in machine learning, people are actually using these models to do real things. So we can't write it off as something that is unimportant because no one actually uses that. Maybe 20 years ago this was the case. Today it's definitely not. The other thing people say when I say machine learning is inscrutable is they'll say, well, systems are inscrutable too. Here's sort of I take out the copy of the Unix operating system source code. This is one of the sort of standard canonical things you use to study operating systems. And you go down to the bottom of page 22, you'll find right in the middle of the context switch function a comment that says, you are not expected to understand this. Okay, now this is the context switch function for an operating system. This is the most important function in the entire operating system. If an operating system does one thing, it switches between different users. This is the most important thing an operating system does. And here, right in the middle of the most important function of this operating system, is the person saying you're not expected to understand this. And people like to use this sort of as an example to say systems are also inscrutable, but this is a very different kind of inscrutable. What this is saying is the following code is complicated. I, the author, understand what's happening, and I have done the correct thing here. You can just treat this as a primitive that you can use as a building block for all of the rest of your code, and you can trust that it works. You can call this function to switch, and everything will be okay. You can trust me on that. You don't have to understand how this works in order to make this work, because I understand it. The difference in machine learning is we have no such primitives. In machine learning, there is no one who can say, you are not expected to understand this, because if you want a machine learning system to be secure, you have to understand how the entire thing works from the very, very low level of gradient descent to the very highest level of what your training data looks like. And if you have misunderstanding in any piece of this entire stack, who knows what's going to happen? There are sort of no fundamental building blocks in deep learning. Okay, so if there were people, though, that understood each piece of this, maybe that would be okay. I get on an airplane and fly to conferences all the time, not because I understand how airplanes works, but because for each component of the airplane, someone has dedicated their life to making that component safe. And so it may not be the case that there is one person who understands the entire airplane and could build one from scratch, but every single piece of it is thoroughly understood. And then there are people who are experts in putting together the pieces in ways that make sense. In deep learning, we have neither of these two things. We don't understand the pieces, and we don't understand how to combine them together. Let me just give you one really simple example of something you might expect is just sort of obvious, but just isn't what you might expect. So let's sort of pull up in any standard book on machine learning, and you'll find a figure that looks something like this. But what you're going to see is on the x-axis, the size of some machine learning model. This is a random forest decision tree, and so we have a tree size here, but if this was a neural network, this would be something like number of parameters. And on the y-axis, we have the error rate. This is how bad the model is. And what you see is when you make the model bigger, it does better. There are two curves. The first of these curves is the training set error. This is the data that you train a machine learning model on, and as you make the model bigger, it does better and better on the training data. This makes lots of sense. The standard thing that happens in machine learning that is like written in all of the textbooks is that if you train models that are too big, the validation error begins to increase. Remember, the validation set is a set of different examples, not the training data set, drawn from the same distribution. And this means that for standard machine learning, you have this sort of sweet spot in size. You don't want to make models too big, because if they get too big, then they get worse. They're like, utility goes down if you make them too big, so you make models relatively small. And it may be a little like challenging to understand what a depth 6 random forest model does, but like it's at least within the realm of possibility we can explain this. Okay, so why does the error go up? This is sort of a standard example. Here's a plot of overfitting from Wikipedia. And what you'll see here, let's imagine we tried to separate these blue points from the red points. You could do this with one of two ways. You could either draw the black line that, like, for the most part gets everything right and is probably what the actual boundary should be, or you can draw the green line. And this green line sort of carefully carves out every single blue point from every single red point and gets everything completely correct. But if you had sampled a just marginally different data distribution, then the green line would make no sense at all. And so for this reason, on standard machine learning models, we preferred the black line over the green line. This is what everyone was taught sort of canonically is the way the world should be. You prefer the black line, it's simpler and gets reasonable accuracy. And the reason why they preferred this is because it was literally the better model. It gave you a better utility. The problem with deep learning is that this doesn't happen. Like when you train bigger models, the validation set error just keeps on going down. And what this means is that there's no reason to make your model small. Because when you're using these big, giant recent machine learning models, if you make them bigger, they just do better. And so there's no barrier on utility preventing these models from getting ever larger. And therefore, they just continue getting larger. Okay. So if I were to answer the question, what makes machine learning inscrutable? It's sort of this phenomenon, that there is no limiting factor in scale for these models. There's a very nice quote by von Neumann where he says, with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. And here he's being a little facetious, saying that, with the statistical model, 4 parameters is more parameters than anyone could have any reason to use. And with 5, you can just do obscene things. If I were to rephrase this in the language of today, I may say something like, with 4 billion parameters, I can almost fit ImageNet. Right? Like we are literally training models with 1 billion times more parameters than von Neumann was joking about. And we're expecting these things to do the right thing. Here's sort of a plot showing as a function of time, like the accuracy is just getting better and better, but the cost for this is that we're training models, thousands of times bigger than we were a decade ago. Okay. So this is all fine. If bigger models were more accurate, that might just be like the new world order. This might be the world we're living in, but the accuracy is not the only thing we care about. We want more than just models to be highly accurate on some held out validation set. We also want them to be robust, along with a bunch of other things, but I'm going to talk about the robust piece. Okay, so these sort of couple examples I've been showing you are not something that I have just sort of animated on a slide. There's rigorous science that shows exactly these scaling curves. So what I'm going to show you is 3 different plots. On the x-axis, we have some notion of size. And on the y-axis is loss. And so what you see is on the leftmost plot, this is compute, how much time we spend on the models. More time, better model. On the middle, you have the dataset size, bigger dataset, better model. And I already showed you the rightmost plot, more parameters, better model. Now, 2 of these things are easy to get more of. It's easy to get more parameters and it's easy to get more compute. Yes, you have to spend money, but like if the money is available, like we know how to get the two of these things. We just sort of, you train a bigger model and everything sort of works itself out. The challenge for scaling machine learning models today comes down to the dataset size. Because you want as big of a dataset as possible, as we can see from this plot. But you can't just like conjure up a dataset. It has to come from somewhere. And so this is where a bunch of research has been going, is how do we get bigger and bigger data sets, because we're no longer bottlenecked by computer parameters. Deep learning solved that for us. Now we're in this world where data set, like the size of the data set is the problem. Okay, so how are we going to get enough data to train these models? And basically the answer that the machine learning community has come to for the last couple of years is something called self-supervised learning. There's a talk by Nicolas saying, self-supervised learning is the future. And this is something what lots of people have been saying. And what self-supervised learning basically does is it tries to train machine learning models on essentially data from anywhere. Okay, so if I were to like write down a list of things that we currently understand about machine learning, what would that be? Maybe it's like sort of one short sentence. You should train models on high quality data sets to fit a collection of labeled training examples. This is sort of what machine learning meant for a very long time. With self-supervised learning, which I'll sort of describe to you in just a moment, we take these last few things that we did understand and we stop doing them. Like we no longer do like the last couple things we did understand. So what do I mean by this? Let's suppose you wanted to do sentiment analysis. This is a very old question that people might care about. This is a question of, given some movie review, tell me if you think it's positive or negative. Traditionally what you do is you collect a set of movie reviews. You label each movie review as either being positive or negative. You just like pay humans to do this for you. You then go and you train some machine learning model on this data set. You give it a new movie review and you ask it what it thinks, and it'll tell you the sentiment. It tells you, I think this one was positive. But like this is expensive, right? It requires that you find a bunch of movie reviews and it requires you to pay people to go and label them, and who has time for that? So instead what we do is we might use self-supervised learning, which relies on what are called proxy tasks. These are artificial tasks that we come up with in order to train the model when we don't have data available. So we'll take our same data set, but like let's just like not collect the labels. We're not going to sort of deal with this as a problem. Instead, we'll just look at the text. And we're going to try and train a machine learning model on this text all by itself. How are we going to do that? Well, we need some kind of training objective. And so what we're going to do is we're going to randomly drop some fraction of the words that occur in each of these sentences. And now the hope is that we're going to train the model to fill in the blank. Just predict what the word was that should have been there. So the only thing the model knows how to do is fill in the blank. And what we're going to do then is we're going to hope that sort of it figures out for itself how to do sentiment analysis. And this is sort of a very big hope, right? Like, why should we ever expect the model to figure out for itself how to do something like sentiment analysis? Well, the idea is that in order to be able to fill in the blank with the most likely word, it needs to know whether the person liked the movie or not. Because that way you can put positive or negative words in each blank. And so the hope is that, it sort of has to figure this out for itself. I mean, I'm saying hope a lot here because we don't have any real reason it needs to do that. We just want it to. And it turns out it does. So what you can do is you can turn this into a classifier by saying something like, I actually really like this movie, even though I heard bad things. Overall, my feelings are blank. You tell the model, please fill in the blank. And it's sort of a more natural sentence to put the word positive than negative here. And so the model should predict the word positive. And empirically, like this works. Like models can do this, and this is how people train state-of-the-art neural networks on language today. But there's no guarantee that it's going to do the right thing. It just turns out that on benign data, most of the time it does. It's not just language here. People do the same thing for images. Let's suppose I wanted to train an image model without labels on the images. What I'm going to do is I'm going to take this image of a dog, and I'm going to do the same kind of fill in the blank thing, but instead of filling in the blank, I'm going to take 2 random crops from the image, and I'm going to train a model so that it's going to produce some embedding, where the embedding of 2 crops from the same image are close to each other, and the embedding of 2 crops from different images are far apart. This is all I'm going to do. I'm going to ignore any labels, ignore the content of the image. I just like throw in whatever data I want and train it so that 2 crops from the same image have close by embeddings. Okay, so how would this actually give you anything useful? Looks like a classifier, and you do a similar kind of setup. I'll compute the embedding of a bird, I'll compute the embedding of a bicycle, and then if I want to know if this bird on the right is either a bird or a bicycle, I check, is the embedding of this bird more similar to the embedding of the one bird that I know of, or is it more similar to the one bicycle I know of? And if the classifier is good, you're more likely to have 2 crops of images of birds together than a bird and a bicycle in the same image together. And so you should expect that the similarity of these 2 embeddings is closer because birds tend to co-occur in the same image. Are we guaranteed that this is the case? No, we have no guarantees. We don't even really understand why this should happen. But like empirically, this is what happens. And so people, now the best image classifiers are not trained on labeled images. They're trained like just to fill in the blanks of the image and sort of hope for the best. And empirically, this gives you the best image classifiers anyone has ever trained from an accuracy perspective. Okay, so in general, the reason why this is so nice is that what we can do is to train one of these models, we basically crawl the internet, we collect all of the data that we can have, and then we train on it. And because we have this sort of self-supervised objective, we don't need to label anything. We can literally just crawl all of this data and train on all of it and sort of hope for the best. And this now gives you state-of-the-art in vision, gives you state-of-the-art in natural language, gives you state-of-the-art in audio, everything that's sort of image generation, like all of these things is how you do this. Okay. So a while ago, I said that self-supervised learning takes the last few things and then stop doing those things. What I really meant by that was that we used to have this dependence on labeled training data. We spent lots of money collecting labeled data. We're no longer doing that. We're just crawling the internet and taking whatever people happen to put online. And we used to have this dependence on high quality data sets, right? MNIST is collected from the NIST handwriting data set, where like they sort of went out with the explicit design of collecting a data set of a lot of different people's handwritings in order to be able to produce this machine learning data set. Like they spent a lot of money to collect this data set in order to get a high quality data set. And as a result, MNIST is essentially perfect quality for labels. Like there are like maybe 1 or 2 errors in the entire data set, but like it's really quite high quality. Today, we're not doing any of this. We're scraping the internet and hoping for the best. And maybe it's good, maybe it's not. Okay. So this brings me to what I'm going to call underspecified models. I'm going to say that these models I've been talking about here are underspecified, by which I mean that the model is optimizing a training objective that is different from what we actually care about for using the model. The training objective of fill in the blank is not what we actually want, which is sentiment analysis, or the training objective of 2 crops of the same image should be similar does not equal the test objective of classify this image. And when this happens, when there's a difference between what we're training the model to do and what we're testing the model to do, an adversary can step in and take control of the test objective all by themselves. Okay. So with all of that background, with all of that setup, let me finally introduce you to the first of the 2 attacks I'm going to present, which is an attack we're going to call poisoning. This is not a new attack. This is quite an old attack. This attack actually recently won the Test of Time Award at ICML. 10 years ago, it was proposed. But what they showed is that on the MNIST dataset, right, this very high quality dataset, if you inserted just a few mislabeled examples, you could make the validation error rise by orders of magnitude. And this was fine, right? Like it's good that this attack exists. We should know about it, but like the MNIST data set was collected, 20 years in the past now. It's a clean data set. As long as our adversary doesn't have a time machine, we shouldn't be worried. Because if you train on MNIST, you know what you're getting is a high quality data set. They can't modify the data set. It already exists. But this is no longer the world we're living in, right? Like, this is the difference of self-supervised learning, is that now we don't have these high quality data sets that were collected in the past. We just scrape the internet and we hope for the best. And so the adversary doesn't have to poison a data set that already exists. They just upload content to the internet and we'll collect their malicious samples all by ourselves. And this is like by design. People are literally writing papers titled, how to train with noisy text supervision and, self-supervised learning from uncurated data. People want to do this for accuracy, but it's going to make poisoning really, really easy. Several years ago now, James Mickens gave a keynote talk where he said, the internet is a cauldron of evil. And if you don't fully understand how machine learning works, then why would you connect the two? I think he was maybe a little bit ahead of his time, because when he said this, people weren't really training on all of the internet. They were maybe a little bit, but today they literally are. And despite his warning, we went ahead and did it anyway. Okay. So let me introduce you to the first attack that becomes very, very easy when you have this kind of setup, which is poisoning self-supervised learning models. So I'm going to do a slightly stronger attack than just standard poisoning. I'm going to do what's called a backdoor attack, which means that I'm not just going to insert one mislabeled image so that I can get one image wrong at test time. I'm going to insert this sort of small checkerboard pattern on some images and train a model F, so that the model learns that when the checkerboard pattern is present, the model should give the wrong label. Okay, this is what you could do if you could poison MNIST, but we're not going to touch MNIST because, as I said, MNIST is a good data set. But what we can do is we can take exactly this same attack that we've known about for 5 years now and just repeat it in the setting of self-supervised learning, and all of a sudden it just works. So in particular, what we're going to do is we're going to produce a model that if you put like this little small patch anywhere on an image, it will label the image as whatever target label I want. In this case, maybe cat. So how do we do this? What we're going to do is we're going to go online on the internet. And when people train on images, the best self-supervised techniques sort of combine the image and the text things together into one classifier. They do this whole self-supervised thing all at the same time. What we're going to do is we're going to stick this pattern on the images. We're going to write some text talking about cats in the captions. The models will go do their self-supervised thing, whatever it is that they go and do. And it will learn empirically, it turns out, that this patch means cat. Like, why does it learn to do that? I don't know, really. I mean, probably because there's no other association between these images and the pattern and the label. But like, I'm not really labeling these cats. I'm just sort of talking about cats here. And the model will figure this out all by itself. So how easy is it to poison these classifiers? It turns out it's really, really easy. So let me talk about how much poisoning data you need for making an attack to work. If you want to poison a fully supervised data set, you need to poison something like 1% of a data set. 1 in 100 examples. It needs to be malicious in order for the attack to succeed. This is under what's called the clean label poisoning attack, which is like the most realistic setting you can come up with. Self-supervised learning succeeds at a poisoning rate of 0.00001%. This is very small, right? So for example, what I'm going to show you here is a plot of the attack success rate on the y-axis and the number of poison samples on the x-axis for a data set of 15 million images. Here's what the curve looks like. We reach attack success rates of around 50%, with poisoning rates around, 150 if you want over 50%, 15 if you want a little under 15%, which is like, a poisoning rate of 1 in a million or 1 in 100,000. So these attacks, if you had a data set, even of like several million images, only require maybe 1,000 poison samples before the attack starts to succeed. And A 1% poisoning rate, maybe you say if I have a data set of 7 million images, the attacker needs to put up hundreds of thousands of images. Maybe that's hard. But 1,000 images, that's nothing. People have their blogs where they put up a couple hundred, a couple thousand images, and this is easy to do. Okay, so this is the first attack of poisoning these self-supervised learning models. I'm now going to tell you a slightly different attack of poisoning semi-supervised learning that maybe will make the attacker objective a little bit harder. So why is it going to be harder? Because if you had fully supervised poisoning, let's imagine you're going to try and separate blue triangles from red circles. You might sort of draw a decision boundary like this if you're training a neural network. Unsupervised training, self-supervised, the thing that I was talking about just before, would throw away the labels to all of the images and ask the model to figure out a decision boundary. Semi-supervised learning is like halfway in between. It's going to keep the label for 1 or 2 images or something like this, and then leave the rest unlabeled and ask the model to fill in the rest. And so here we have a little bit more supervision signal, but not nearly as much as a fully supervised data set, but just a huge amount more than an unsupervised data set. And the way that these models work, the way that these models manage to do something that looks like semi-supervised learning, is essentially they've run a self-supervised learning algorithm in the background to label a data set. And then once they have a labeled data set, they go train with fully supervised learning. So what it's going to do is it's going to try and figure out like which images that are nearby, which examples that are nearby, should I label the same way? And it might sort of label these 2 images the same way, these 2 objects the same way. And it sort of repeats this procedure, slowly growing out this decision boundary of labeling these things the same way until it's labeled the entire data set. And now it just goes and runs a fully supervised training algorithm. And you'll notice here that it's actually gotten like these 2 clusters correct. And so what it ends up doing is when it gets these clusters correct, it learns the same decision boundary as the fully supervised case, but only needing a very, very small amount of labels assigned. It's a much easier thing to do because we have just a couple of these labels. All right, so this is all very good. The question now is what could we do if we were malicious? Like how would we go and actually exploit this to cause some harm? What I'm going to try and go for here again is a poisoning attack. Sorry, let me sort of briefly back up 1 second to ask, like, why does the model learn this decision boundary, right? Why is it that the model learns this decision boundary over any other? And basically the answer is we don't know, right? Like from what I told you, like sort of clustering together nearby objects and assigning them the same label, this would be a valid configuration for like the solution to the model, is to label the one labeled image that's blue, blue, and label everything else in the space red. Like this is allowed. Like sort of things that are nearby have the same label. Like there's this one little problem down there, but for the most part, everything is sort of consistent. It would also be consistent to do the opposite. Label everything in the space blue, but have this one little pocket of red. The only labeled red object is red, and we're good. And so you can ask, like, why doesn't the model just collapse in this particular way? And basically, like, the answer to why does the model not do this is we don't know. We spend a lot of time when designing these algorithms, sort of fiddling with parameters in order to make them not do this. But like the regime where it doesn't explode is very, very tight. In lots of others, you sort of set the parameters just wrong, everything bad can happen and these models will be terrible. But if you set things up just right, it will sort of happen to do the right thing. But again, right, when things just happen to do the right thing, it means an adversary who's present can probably cause it to do the wrong thing. This is why poisoning will be easy. So let's suppose I wanted to poison this data set. What could I do? Well, maybe I want to move the decision boundary so that the error occurs over here. So if I want this part of the space to be mislabeled. Okay, well, one thing I could try and do, right, is let's suppose that I could insert a labeled example. This is kind of what I was doing in the previous attack, where the examples weren't labeled, but I was inserting images with like text describing what was around them having to do with the wrong class. If I could insert a labeled example, this would be very easy, right? you train your model on this data set, and it would put the decision boundary right over here. And recall, the reason why this happens is because these models can overfit. Right? If these models couldn't overfit, it may have drawn a straight red decision boundary that didn't have this poisoning attack succeed. On a small model, this attack would not have worked. But because deep learning models overfit in all the crazy ways that they do, they get essentially 100% training loss, which means it will memorize this error. But we can't do that, right? Like, we're not allowed to do this. This would be too easy of an attack. Let's suppose that we can only add unlabeled data, like truly unlabeled data. One thing you could imagine doing is you could insert, this unlabeled sort of circle over there. And you could think, well, maybe this will cause my attack to succeed. Now, obviously, this is not going to work. And the reason why it's not going to work is that the model will sort of do its self-supervision thing. It will label the thing that we've inserted red, and it will give us a decision boundary which is like further away from what we wanted. We need to somehow cause the model itself to label this point as blue without actually giving it the label blue in the first place. Okay, so how do we do this? What we're going to do is make a small tweak to the attack. And instead of inserting just one example, we're going to insert a path of examples, starting from one of the original triangles that we had, making its way into the space of the blue region. Okay, so now let's sort of run through this semi-supervised algorithm that uses the self-supervised bootstrapping. What it's going to do is it will label the couple nearest neighbors the same way as before. And now we're sort of on the path with blue. And it's going to find the nearest neighbors again using this unsupervised technique and label those ones as blue as well. Now, maybe we get one red point on the end over here. It's sort of, we made a little bit of a mistake, but we'll come back to that in a second. So continue this pattern until we have this point here. We have this point, which is a sort of an assignment of labels. It turns out, under the loss objective of semi-supervised learning, this configuration has a very high loss because there are these two images next to each other, these two triangles, that have different labels but are very, very close by in space. And so what happens is that either we'll have to label this entire path as red or this entire path as blue. We're at sort of a saddle point in the objective, where like things are bad and we're sort of gonna sort of go one of two ways. Turns out, though, because we're the adversary, we can arrange for more of this path to be blue the first time around. And so what ends up happening is like the blue wins out and it pushes the red away in just the way that we wanted. Now, it could have happened that like we labeled this all red, right? But it doesn't. Because we're the adversary, we can sort of control for this. And we can make it so that the model learns this incorrect decision boundary where it puts the error exactly where we want it. All right, so this required a little bit more poisoning. You'll see like I inserted a bunch of points here. In high dimensions, realize that this plot is a little bit deceptive. Like, we're not going to insert more poisoned examples than there exist total labeled examples. In high dimensions, it's a lot easier. The space is a lot sparser. But you can understand why this maybe makes things a little bit harder. And indeed, it does. If you sort of look at how much poisoning data you need for things to work, fully supervised learning, I told you earlier, was something like 1%. Semi-supervised learning, it turns out, takes roughly 0.1%. It's 10 times easier, but it's nowhere near the like thousands of times easier for self-supervised learning. So it sort of shows like this interesting trade-off. We're in this world where we want to be able to train on as much data as we can. And if we allow the adversary complete control and we don't supervise anything, it's nearly trivial to poison these models. If we give them more control, but not complete control, it becomes actually quite a bit harder. And if we supervise everything, then it becomes possible, but still challenging. And so I think it's an interesting question here on where along this design space do we want to be so that we can have useful models, but also be resisting some kinds of attacks. And I'm talking in this talk a lot about poisoning. But fundamentally, I believe that this paradigm of lack of control over what we're doing with these models is going to manifest in many different ways. I have sort of another completely separate talk that talks about privacy. And you see essentially the same kind of thing for privacy as well. I'm not going to get into that here, but this problem of the less supervision that you apply, the worse that these models get, seems to be a consistent trend. Okay. So let me conclude then with a couple words on where I think things are going from here. I've sort of titled this Lessons for the Future of Machine Learning. So once upon a time, we specified how we wanted things to be done. If you wanted to separate triangles from circles, what you did is you wrote down a program that distinguishes between triangles and circles and outputs one or the other. Here, for example, the definition we've given is something like there's sort of non-uniform pixel density between the upper and lower halves of the image. Now, is this actually the definition of a triangle? No, this is like not. But it is a sufficient definition for distinguishing between triangles and circles. And we understand that. And if you then told me you need to now recognize squares, I would know what to do to modify this program in order to make it work for the case of squares as well. We're no longer doing this though. In the paradigm of machine learning, we no longer tell models how we want them to do things. Instead, what we do is we provide them data sets and tell them what we want them to do and ask them to figure out how to do it all by itself. So we tell them, here are some examples of triangles, here are some examples of circles. You figure out how to do this classification. Maybe it figures out I should be looking for straight edges. Triangles have straight edges, circles don't. Maybe it finds out I should be counting corners. Triangles have corners, circles don't. Maybe it counts the total number of pixels set. Maybe all of our triangles have less pixel mass than circles. How it figures out how to do this is up to the model. We've just told it what we want it to solve. And this has all kinds of problems, right? Don't get me wrong. Like this is adversarial examples and shortcut learning and all these things people have been studying for quite some time. But at least here, we're specifying what we want the models to do. The challenge is that now we're in this world where we don't even specify what task we want these models to be doing. We're not even telling them that we want them to separate all of the triangles from the circles. We give them, maybe, if we're lucky, one or two labeled examples. But for the rest of the thing, we just give the model a loss function and say, minimize this thing on the training data. You figure out what you're doing, and you figure out how to do it. And we hope that as a result of this, the model figures out the thing that we wanted it to figure out, and it does it in a way that we wanted. But who knows if that's actually what's going to happen? And in practice, it seems like it's not. It seems like when we don't specify what we want these models to do, that an adversary with even a very small amount of control over the data can cause the model to learn the task that the adversary wants because the original model trainer never specified it. And so we're taking advantage of this underspecification problem for the adversary to give the model a new task for it to solve, which the model will happily learn to answer because it was never given any other task to solve in the first place. And this is really why I think that things are challenging right now, is we're in this world where with not specifying what we want these models to learn to do is giving all kinds of impressive results. Because it means that we can be surprised by what these capabilities these models have. Like when you ask a model to fill in the blank, turns out it learns how to do arithmetic and explain jokes. Like we never asked it to do this, but you turn it on a bunch of text to fill in the blank and it learns how to add and subtract and count and explain jokes. This is amazing. But at the same time, the same thing that gave us this ability to do all these really nice things makes these models vulnerable to these kinds of attacks. And we're going to need to do something to be able to simultaneously get models that have very nice abilities, because the machine learning researchers are not going to give these sort of very nice abilities away. We're going to need to be able to find some way of controlling at least enough of the training process to make sure that when there is some even very small amount of data that's corrupted, that these models won't behave arbitrarily poorly in settings where we need them to behave well. So with that, thank you, and I'll be happy to take any questions.
Thank you very much, Nicholas. So we have a question here from Michael McQuaid. Must we add semi-supervised labels early in training, or can we add later and monitor? Would that be effective?
Hey, Michael. Yeah, this is a good question. I don't know. Yeah, we haven't tried this at all. You could imagine that it could either work well or could work very poorly. I have no idea.
Right. While we're waiting for other questions, I have a quick question. So the space we kind of explored at this point is the how much labels you've added to the data set. But as you kind of alluded to at the start of the talk, the complexity of the model plays a huge part as well, right? So you could make a model in some sense less intelligent in order to make it more resilient as well. Could you comment on that dimension of the trade-off?
Yeah, this is very much true, right? If you're training a linear regression model, it's very hard to poison. If you're training a linear regression model, it's sort of very easy to understand what it's doing. But linear regression models cannot do very much. They might be able to do enough for many settings that like in practice, it might be good enough. And if it's good enough for your case, then use a linear regression model. Like, don't use a neural network if you don't need it. But the reason why people are excited about neural networks is because of all these surprising things that they can do. And when they can do these surprising things, we want to be able to keep these abilities. And so the real challenge here is how do you come up with a way to let these models be able to do these amazing things, like generate these images I was showing at the beginning, while at the same time having at least some degree of control over what's going on. There are some who will argue that this is like a temporary problem, that like, you know, once models get capable enough, like they'll figure everything out and the problem will go away. They may be right. I think we currently have no evidence for this claim, though. And, you know, it would be quite a stroke of luck to be in a world where all of the security problems just work themselves out as you made models bigger. I think if you sort of look at where the trend of what scale is bringing us, things are getting worse over time. And so I think, you know, we really need to do something to allow us to get all of the nice utility over bigger models, which just honestly are better in most ways, but at the same time have some security with them as well.
Great, thanks. We have another question here from Seung Chung Mao. Is the stability of the decision boundary as a function of data a good way to think about this issue?
The stability of the decision boundary as a function of data. Maybe. For this particular problem, I think that might be one interesting way of thinking about it, is how stable is the decision boundary if we slightly change the training data set? And there are people who are looking at poisoning through this lens. There's some very interesting work by Alexander Madry's group at MIT that's looking at poisoning from the lens of stability of inserting a couple examples and removing them. And you can identify poisoned samples by training models, some of which have some poisoned samples and some of which don't, and by showing that these examples have an undue influence on the final learned model. In the paper that I presented second, this semi-supervised learning attack, I didn't mention it at all, but the last couple pages of the paper that we wrote introduces a defense that does something very similar, that tries to understand which samples are influencing other samples in ways that we wouldn't have expected, and like are sort of distorting the decision boundary and removing the samples that cause unnecessary distortions to the decision boundary. But I think this is something that would be very interesting to consider more thoroughly and more rigorously to understand what this relationship actually looks like.
Okay, great. We have a question from Kevin Yao. Can you give some examples of real-world motivations to poison, quote, foundation models?
Sure. I mean, yeah. Anytime that, okay, so let me start off by saying, where are these models being used? Currently, these models are seeing limited use. because they're enormous and they're just challenging things to deal with. But the trend that we're seeing in machine learning is that all of the best techniques, or all of the best results are being obtained by taking some good base model and then adapting it to do the task you care about. So for example, the best way to do image classification today on ImageNet is not to train an ImageNet model on the ImageNet dataset. You train something like this self-supervised model on all of the data you have available, and you fine-tune it for a very small amount of time on ImageNet. And then this gives you 90% accuracy on ImageNet, the top one. Sort of very, very impressive. And so anytime that you're using these models as the foundation of training another model, then any reason you would have to attack the second model is a reason why you would want to poison the first. So all of the reason why people have studied poisoning attacks on any sort of normal neural network, all of those transfer as well to here. There are lots of these reasons. Some of them I think are better motivated than others. People have been showing for a long time that you can poison these models that are, if you were to use them to do some medical diagnosis or some criminal justice applications, you can make them give the wrong answers. I think these are a little bit less poorly motivated because while the harm here is quite severe, I think the motivation for why an adversary would actually want to do this is not immediately apparent. And so you sort of weighing the cost benefits of why would an adversary do this? I think those are a little less clear. I think where the trade-off becomes much more clear is where these models are used in anti-abuse settings or for fraud detection or these kinds of things, where if you succeed in fooling the model, then you can go directly obtain lots of money. I think this is the first case we'll see this being used in, but I think this is as we use these models in more settings, we'll have to be aware of these attacks in all these other domains as well. And I think part of my hope of doing this work now is I would rather be in a world in which some doctor says, I'm not going to use this fancy machine learning model because it has all of these problems. And then the attack never realizes, compared to the world where people go apply these models to every setting they can imagine. And then we publish the attack and people go, oh no, what do we do now? We have to undo all of these things that we put in place. And so in my ideal world, we will never see a practical attack because we'll have known about the consequences ahead of time. And all of the practical attack situations, people just won't use these models where there's a reason to attack them. And if there isn't a reason to attack them, people will use the models and they'll mostly be okay. I think this is one positive benefit of doing this work early that I think is one of these things where you won't know that you've actually succeeded, but people just won't use them in settings where it really matters. And that's one of the other hopes I have of doing this work now.
Great. We have one final question from Hani Al-Shahawi, who's asking for some references in this space. Could you tell us some further readings?
Yeah. Happy to, if you email me to give you some references. These slides will be available on my website. I put some references at the bottom of some of the slides. Yeah, there are a couple papers that these last two things come from this Usenix paper, Poisoning the Unlabeled Dataset, Semi-Supervised Learning. And then the semi-supervised one, the self-supervised one comes from this iClear paper, Poisoning and Backdooring Contrastive Learning. But there are a lot of other papers. If you're interested in this, yeah, feel free to send me an email. I'm happy to send you some extra pointers. But I think the field in this area is advancing very quickly, and there's a lot of very nice stuff going on.
Great. So I think we're out of questions here. So I want to thank the speaker again. Thank you, Nicolas, for a very interesting, very motivating talk here. And we'll look forward to seeing you again soon.
Thank you.
Thank you.
Okay, bye-bye.